Welcome back to my YouTube channel. Today I will solve a question of JAM exam. Okay, question is say that V is a non-zero vector space over a field F and let S be a any subset of V which is non-empty. Then consider the following statement. Here given four statement, then which of the following is true? Okay, now first option. Now solution. Now option E. 1 implies statement 1 implies statement 4. Statement 1 say that for any vector W over F, okay? So for any vector W over F, okay? And any map, and T is any map F from S to W, okay? Extend to a linear map from V to W, okay, and say is F tilde, okay, linear map. Then this implies statement 4, that is span of S equal to V. Now check. Okay, now first of all let dimension of V equal to some 4, okay, and dimension of S equal to 2, okay, where is a we choose S is a surface of V, okay, 2-dimensional surface of V, okay. So there exists a basis of S. So let suppose beta 1 and beta 2 is a basis of S, okay, and S is a surface of V, that is every element of S also element of V. So this implies this is a basis beta 1 and beta 2. So this is also Li set, that is linearly independent. So we know that any linearly independent set can be extended to a basis of V, okay. So beta 1 and beta 2 can be extended to a basis of V, okay. So say this basis is called beta 1 beta 2 beta 3 and beta 4, okay, that is 4-dimensional we choose, okay. Here V is 4-dimensional, so is a basis of V, okay. And we know the result. If beta 1 dot beta n is a basis of V, okay, and W1 dot Wn belongs to W, that is subset, any subset which is not necessarily basis, okay, any subset of B of W, okay, then there exists a unique linear transformation, okay, from say T, that is V to W, such that T of beta 1 equal to W1 and dot T of beta n equal to Wn, okay. This is a result, famous result, okay, using this result in this problem, okay. Now so here basis of V is, here this is a beta 1 dot beta 4 is a basis of V, So we can find a unique linear transformation from the above result. Okay, so there exists a linear transformation, okay, unique linear transformation from TV to W, T of beta I equal to Wi. Okay. Okay, now we choose F is a map, okay, from S to W. Okay, here given in statement 1 any map here. Okay, so we have, this is my any map, so we choose F of beta 1 equal to W1, okay, F of beta 2 equal to W2, and others element anywhere map. Okay, F. So, and this is a linear map. Okay, now we check this T, this linear transformation is extension or not. Okay, T of beta 1, this value equal to W1, so this is from this equal to F of beta 1. Okay, and also T of beta 2, this equal to W2, this equal to F of beta 2. Okay, so this implies T of beta I equal to F of beta I. Okay, so every basis element image are same. Okay, so we also know that if two linear maps are agree on basis, then this is a also agree on this set, whole set. Okay, so clearly T is extension, T is an extension of F. Okay, but here dimension of S equal to 2. Okay, so this implies span of S not equal to V, since dimension of V equal to 3. Okay, so this is a false. And here also choose F is a linear map. Okay, linear map. Okay, and which satisfy the following condition. Okay, then we can choose this function as follows. Then we have span of S not equal to V. Okay, so option A is false option. Okay, and here use is agree on the basis, then the linear map agree on the whole set. Okay, this result use here. Okay, this proof is very simple. Suppose any beta belongs to S. Okay, so beta is can be written as linear combinations of the basis element. So beta equal to alpha 1 beta 1 plus alpha 2 beta 2. Okay, now T of beta. Okay, T of beta, so this equal to T of alpha 1 beta 1 plus alpha 2 beta 2. Okay, so this implies now separation and using linear property. So we have alpha 1 T of beta 1 plus alpha 2 T of beta 2. Okay, and this is equal to F of beta 1 from here, and this is equal to alpha 2 f of beta 2. Now using linear property of f, so we have f of alpha 1 beta 1 plus alpha 2 beta 2. So this equal to f of beta. Beta is arbitrary, so for all beta belongs to S. Okay. So option number A is false. Now second option. Option number B is say that say statement 1 implies statement 3, that is for any vector space W over F and any linear map can be any map can be extended to a linear map from V to W, then we say S is linearly independent. Okay, now check option B. So V is a subspace over F, okay, and also given F is any map from S to W, okay, extended to a linear map F delta on V to W. Okay, so then this implies S is Li or not. Okay, now check. Suppose S is not Li, linearly independent. Okay, so this implies S is dependent, linearly dependent. Okay, so that means some vector x1 x2 dot xn belongs to S such that alpha 1 x1 plus alpha 2 x2 plus dot plus alpha n xn equal to 0 for some, such that for some alpha I not equal to 0. Okay, this is condition number 1. Okay, now here given F is any map. Okay, so we choose if S2W, okay, by with some property f of xi map alpha I conjugate into W for fixed W non-zero. Okay, W is non-zero vector, not equal to 0 vector belongs to W. Okay, and other element anywhere maps. Okay, and other elements, suppose f of x belongs to W anywhere maps where x not equal to xi. Okay, this is a map, well defined map. Okay, and now statement number 1 is say that this is extended to a linear maps. So suppose f tilde is the extension of f. Okay, so that means f delta xi also equal to f of xi, because all xi belongs to S. Okay, so this equal to alpha I conjugate into W. Okay, so now from 1 x1 alpha 1 plus x2 alpha 2 plus dot plus xn alpha n equal to 0. Now applying both side in this linear operator f delta. Okay, f delta, that is x1 alpha 1 plus dot 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 plus xn alpha n equal to 0. Okay, now using linear property, so we have alpha 1 f delta x1, okay, plus dot 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 alpha n f delta xn equal to 0. Now putting the value of the each xi from this. Okay, so we have alpha 1 conjugate into w plus alpha 2 conjugate into w plus dot 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 plus alpha n conjugate into w equal to 0. Okay, so this implies mod of alpha 1 square into w plus dot 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 plus mod of alpha n, okay, square into w equal to 0. We know that since alpha I conjugate equal to mod of alpha I square. Okay, so this implies mod of alpha 1 square plus dot 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 plus mod of alpha n square dot w equal to 0. So this implies mod of alpha 1 square plus dot 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 plus mod of alpha n square equal to 0, since w is non-zero vector already chosen. Okay, w is non-zero vector. Okay, so we have this value implies, this line implies alpha 1 equal to alpha 2 equal to dot equal to alpha n equal to all equal to 0, which is a contradiction. Why? Because already given here already given here some alpha I not equal to 0, but here all alpha I equal to 0, so which is a contradiction. And so this, from this, S is linearly independent, S is linearly independent. Okay, so option B is true. Okay, option B is true. Now option C. Now option C say statement 2 implies statement 3. That is, statement 2 say that for any vector w over f and any two linear map f and g from v to w satisfying f of s equal to f of g for all s belongs to s, we have f of v equal to g of v for all v belongs to v. So this implies s is linearly independent. Okay, so now check option C. Option C, given w is a subspace and also any two linear map f and g. Okay, any two linear map f and g from s to w with f of s equal to g of s. Okay, for all s belongs to w. So then then we have f of v equal to g of v for all v belongs to v. Okay, so this implies s is linearly independent. Okay, so this is true or false. Okay, now check. Now we choose here we choose S is a subspace of V, okay, and 0 comma beta 1 comma dot dot beta n, okay. Now S equal to choose this, okay. Here sorry, S is not a subspace, we choose S equal to 0 beta 1 beta 2 dot dot beta n, okay. Here beta 1 dot dot beta n is a basis of V, okay. Now we choose as follows S. Now given f of S equal to f of g of S, so that is f of beta I equal to g of beta I, okay, for all I equal to 1 to dot n, and also f of 0 equal to g of 0, okay. So now this beta 1 comma dot dot beta n is a basis of V, okay. So any element V belongs to W can be written as a linear combination of the basis element. So V equal to alpha 1 beta 1, okay, plus dot dot plus alpha n beta n, okay. Now f of V, okay, and here given f and g are linear map, okay. So f of V, that is equal to f of alpha 1 beta 1 plus dot dot plus alpha n beta n, okay, that is equal to alpha 1 by linear property of f, that is equal to alpha 1 f of beta 1 plus dot dot plus alpha n f of beta n, okay. Now using this is star, using star, from star this is equal to alpha 1 g of beta 1, okay, plus dot dot plus alpha n g of beta n from star, okay. Now using linear property of f, so we have g equal g into alpha 1 beta 1 plus dot dot alpha n beta n, that is equal to g of V, and V is any point, any vector of V. So this implies f of V equal to g of V for all V belongs to V, and also given f of 0 equal to g of 0 already given. So for all V belongs to V, this is hold, okay. But still here S is not Li, linearly independent, because here 0 vector content this set S, okay. Any Li vector does not contain 0 vector, okay. So this implies option number C is false, okay. Now option D. Option D say statement 2 implies statement 4, okay. Statement 2, this is already discussed, so this implies span of S equal to V, okay. Now check option D. Option D given W is a vector space over F, okay, and any two linear map F and G, okay, from V to W, okay, V to W, and satisfy f of S equal to g of S for all S belongs to S, then we have f of v equal to g of v for all v belongs to v. Okay, then this implies span of s equal to v or not. Okay, now check. So suppose span, this is called span S. Okay, denoted here this notation. Suppose span of S not equal to v. Okay, so there exists a non-zero vector v not equal to 0 belongs to v such that v1 does not belongs to span of S. Okay, so v1 does not belong to span of S. So and also we know that span of S is a subspace of V. Okay, so suppose beta 1 dot beta m is a basis of span of S. Okay, so here, so beta 1 comma dot beta m is a basis, so it is can be extended to a basis of B. So it is can be extended to a basis of V. Okay, suppose this is say beta 1 comma dot beta m comma dot some here alpha 1 belongs to this. Okay, sorry, v1 belongs to this and some dot vn. Okay, why beta 1 belongs to this? Because this is a Li set. Okay, and if beta 1 v1 does not belong to span of S, so this set beta 1 comma dot beta m, okay, and also v, this is also Li. This is if and only if case. Okay, so beta 1 belongs to basis of V. Okay, so now we defined linear maps. Now we define a map, linear map f and g as follows. All f of beta 1 beta I equal to g of beta I for given condition, because beta 1 beta 2 are element of the S. Okay, for all I equal to 1 to dot m. And also we defined here we defined f of v1 does not equal to g of v1. Okay, we define this because v1 does not belong to span of S. Okay, so we can define this. Okay, now so beta 1 beta 2 dot beta m is a basis of S. So we already above discussion we know that if two linear maps are satisfied on the basis or basis element are equal, then the linear map whole map are equal in the whole set. Okay, so this implies f of S equal to g of S for all S belongs to S. Okay, now above given condition we have f of v equal to g of v for all v belongs to v. So this implies f of v equal to g of v for all v belongs to v. Okay, which is a contradiction? Is a contradiction. Why? Because here already we defined f of v1 not equal to g of v1. Okay, since f of v1 not equal to g of v1 and also v1 also member of v, non-zero members, so which is a contradiction. So this implies from this, okay, this implies span of s equal to v. Okay, so option number D is also true. So therefore answer of the question is B and D. Okay, thank you.